Hello my dear students. Today I am going to discuss the remaining topic of the chapter, the distribution law. In my last video I discussed in detail about the Nernst distribution law, its limitations and thermodynamic derivation. Those of you who haven't watched my previous video, it is a request to them, please watch full video of the part 1 for better understanding of this topic. A link to the part 1 of this chapter is given in the description. Please follow that link to access that video. And before starting today's session, I would request all my new students who still haven't subscribed my channel, please subscribe it very soon and press the bell icon so that they could get the notifications of my new videos. Thank you. Now let us start today's topic, that is modification of the distribution law with change in molecular state of solute. Modification of distribution law with change in molecular state of solute. Means if the solute either associate or dissociate in any one of the liquid, then what would be the partition coefficient or how it would be calculated. So this is today's topic. Let me start with the first case 1. When the solute undergo association in one of the solvent. When solute undergoes association in one of the solvents. Now suppose we have a mixture of two immiscible liquids, that is liquid A and B or liquid 1 and liquid 2. Okay, and a solute X is distributed between these two liquids. Okay, as we know that the distribution of that solute will be different in both the liquids. So suppose C1 is the concentration of the solute, that is X, in liquid 1, and C2 is the concentration of solute, that is X, in solvent 2. Now suppose the solute X remains in the normal state in liquid 1 and it undergo association in liquid 2. So what would be the system then? Then there will be two type of equilibria exist in the two liquids. In phase 1, the X is in the normal state, so there will be one equilibria of this type, and in phase 2 where the solute is undergoing the association, so this type of equilibria will exist in phase 2. What is going to be there in the liquid 2? That the N molecule of X undergo association and forming this type of moiety. Suppose the two X molecules combines and form a one dimer molecule of this type. Okay, Now suppose the total concentration of solute X in phase 1, the concentration of solute is equal to C1 in phase 1. Okay, and in phase 2 let the total concentration of solute in phase 2 is C2. Okay, now I'm taking this equilibrium only. Now suppose initially it is having 1 mole in phase 2 and there is no association in the starting. Now when the equilibrium is maintained between the two liquids, when the distribution of solute X is completed in the two liquids, and at that stage suppose the 1 mole of X in phase 2 undergo association, and now suppose out of 1 alpha is the degree of association of solute X in phase 2, what will be the concentration left behind of unassociated molecules? It will be 1 minus alpha. And what would be the concentration of associated molecules? It will be the alpha by n. Okay, now as we said that the concentration of solute in phase 2 is C2, then we have to multiply with this one. Okay, so this would be the concentration of unassociated, or you can say the normal molecules in phase 2, and this would be the concentration of associated molecules in phase 2. Okay, now applying the distribution law, to the distribution of X in both solvents. What is the distribution law? It is the concentration of solute in phase 1 upon the concentration of normal molecules of solute in phase 2. It will be equal to K. That is, now what is the concentration of solute in phase 1? As we said, it is C1. And what would be the concentration of normal molecules of solute in phase 2? It is this one. So write down C1 upon 1 minus alpha C2, it will be equal to K. So by this way we can calculate the partition coefficient of solute in the two liquids, and that solute undergo association in one of the solvent, and if the alpha is the degree of association, then we can easily calculate the partition coefficient of that particular solute. Okay, now applying the law of chemical equilibrium to this reaction. So what is that? It is the equilibrium constant, which is equal to the product upon concentration of the product upon concentration of the reactant. So it is equal to the concentration of products to the concentration of the reactants. Now using this relation here, so what will be the equilibrium constant? So it will be equal to the concentration of product is what? The concentration of the associated molecules. So we can write C2 alpha by N upon C2 1 minus alpha raised to power N. Okay. So further, taking the nth root on the both side, as we have the K equilibrium is 1 upon N C2 alpha upon 1 minus alpha C2 raised to power N. Taking nth root on both sides, we have C2 alpha upon 1 minus alpha C2, and it becomes the constant. Okay, because the equilibrium constant is a constant value, so taking the root of nth root of a constant is further a constant term. Okay, now we have to divide this equation with the previous equation. Let it a number 2 and the previous equation is number 1. Now dividing the equation 1 with equation 2, we have dividing equation 1 with 2. So what is the equation 1? It is equal to C1 upon alpha 1 minus alpha C2. So it is C1 upon 1 minus alpha C2, which is equal to K. It was equation 1, and C2 alpha upon 1 minus alpha C2 is equal to constant, that is the equation 2. Okay, now dividing both the equation, we get C1 upon these two terms will be cancelled, so we will be having the C2 alpha, okay, K upon constant, a new constant, that means we can say C1 upon nth root of C2 alpha is equal to constant. Okay, now suppose all the molecules, or you can say the total concentration of the solute in phase 2 is completely associated. That means all the molecules of the solute are getting associated in phase 2. Suppose all the molecules of X are being associating in phase 2. In that case, alpha will be equal to 1. Then the equation becomes C1 upon nth root of C2 is equal to constant. Okay, so let it be equation number 4. This equation number 4 can be used for the determining of the value of n. Okay, that is the extent of association of the molecules. This C1 and C2 are the experimentally determined quantity. If we know the concentration of solute in phase 1 and the phase 2, we can easily predict whether the solute in phase 2 is going to be associated or not. Okay, so n can have value from 1, 2, 3 and so on. Okay, let us take the second case when the solute undergo dissociation in one of the solvent. So second case is when the solute undergo dissociation in one of the solvent. Means if we have a mixture of two immiscible liquids and if a solute X is being distributed in these two liquids, and suppose the solute X undergo dissociation in the phase 2 and forming the two ions or the two molecules such as A and B, and let the concentration of solute in phase 1 is C1 and in the phase 2 it is C2, and both the liquids are in equilibrium. Okay, now what is going to be happen in phase 1? As it is not undergoing any association or dissociation in phase 1, so we will be having this type of equilibrium in phase 1, and in phase 2 what is going to be happen? The X is undergoing dissociation and forming two molecules. Okay, as we have considered that the total concentration of X in phase 1 is equal to C1, okay, and the total concentration of X in phase 2 is C2. Now take this equilibrium. Now suppose initially there is one molecules, and after attaining the equilibrium let the X is undergoing the dissociation in the phase 2, so initially it will be 0. When the equilibrium is attained, so we can say at equilibrium position let the alpha molecules of this X, that is solute, is undergoing dissociation. So what will be the left behind? The 1 minus alpha will be X, that is undissociated molecules, and alpha will be this formed and alpha will be this molecule formed. Okay, now what is the total concentration of C2? So we have to multiply, that is C2, C2 and C2. So this C2 1 minus alpha is the concentration of undissociated molecules of solute in phase 2. Okay, now applying the distribution law, the ratio of concentration of solute in equilibrium will be equal to C1 upon C2 1 minus alpha, that is the partition coefficient. Okay, so in this way we can calculate the partition coefficient if the solute is undergoing dissociation in any one of the solvent. Now suppose the solute is undergoing dissociation not in liquid 2 it is undergoing dissociation in liquid 1. So this relation will be changed, as we will write 1 minus alpha with the C1 and C2 will be the concentration of solute in the normal form in liquid 2. So it will be given as by this relation. Okay. And the case third is that if or when the solute undergo dissociation in both the liquids, then what will be the relation, modified relation? Simply, now suppose C1 is the concentration of solute in phase 1 and C2 is the concentration of the solute in phase 2, and let the alpha is the dissociation of solute in phase 1 and alpha prime is the dissociation of solute in phase 2. In that case, we will be having the C1 1 minus alpha upon C2 1 minus alpha prime is equal to K. If we know that how much solute is undergoing dissociation in solvent 1, okay, and how much of the solute is undergoing dissociation in phase 2, then putting the value of alpha, that is the degree of dissociation of the solute in phase 1 and degree of dissociation of solute in phase 2, we can easily predict or calculate the value of K, that is distribution coefficient or partition coefficient. Next we have a case 4, which is very interesting one. It is that when the solute enters into the chemical combination with one of the solvent, that means if the solute undergo a chemical reaction with any of the solvent, then what would be the relation? So I am writing down the case 4, that when the solute undergoes or enters into a chemical combination with one of the solvents. Now suppose we have this type of situation where both the liquids are in equilibrium and both are immiscible, and a solute X whose concentration is C1 in liquid 1, okay, and here it is having the concentration C2, okay. In phase 1 there is no change, and here it is combining with the solvent, it is a solvent 1 and solvent 2. So if we have the concentration of solvent in phase 2 CS, then suppose n molecule of solvents are being associated with the X and forming a complex like XNS, okay. So two type of equilibria will be existed in this system. In phase 1 there will be no change, that is X is undergoing as X, no change. In phase 2, as it is combining with the solvent, so X plus n molecule of solvent, they are combining and forming a combination reaction, combination product. It is like this. Okay, now let the concentration of solute in phase 1 is C1. In phase 1 the concentration of solute is equal to C1, and in phase 2 the concentration of solute is X2, and the concentration of the solvent molecule in phase 2, concentration of solvent is CS. Then when the X is going combination with the solvent, so what would be the concentration of this new complex? Let it be CC. Okay, so I can write in phase 2 the new concentration, that is the concentration of complex which is going to form in phase 2 is given as CS. Okay, now applying the distribution law to the equilibrium 1, that is this equilibrium, so we will be having the C1 upon C2 which is equal to K, which is simply the simple Nernst distribution law. Now applying the law of chemical equilibrium to the second equilibrium, okay, in that case what is the chemical equilibrium, law of chemical equilibrium? It is the concentration of products upon the concentration of the reactant. Now here we have the concentration C2, it is CS, it is CC. So the concentration of the product, that is CC, upon concentration of the reactant, that is C2 into CS, and N molecules are there, so it will be raised to over N. It will be equal to K equilibrium. I am writing here again. Let this equation is number 1. Now applying the law of chemical equilibrium to equilibrium 2 in phase 2, so I can write the CC upon C2 into CS raised to power N, which is equal to K1. Okay, so as we already studied that the distribution law is valid only in case of the dilute solution. So in dilute solutions the concentration of the solvent in phase 2 will be remain same as it is in the excess form. So CS is not going to change, practically constant for dilute solution. Okay, so the equation 2 takes the form as CC upon C2 is equal to K1 into CS raised to power N. So it is a new constant, that is K2, which is also again a constant. Why so? Because K is a equilibrium, K1 is a equilibrium constant, and C as is the concentration of solvent, okay, in phase 2, which is also practically remain constant for the dilute solutions. So multiplying both two constant terms give you a new constant. Okay, write it down, the equation number 3. Now if I add 1 on the both side, adding 1 on both side, we have 1 plus CS upon C2 equal to 1 plus K2. So it will be equal to C2 plus CC upon C2 equal to 1 plus K2. Let it be a equation number 4. Okay, Now dividing the equation 1 by equation 4, dividing equation 1 by equation 4, we get, what is the equation 1? It is C1 upon C2 upon K. What is the equation 4? That is the C2 plus Cs upon C2 is equal to 1 plus K2. Now if we divide, it will becomes C1 upon C2 into C2 upon C2 plus Cc equal to K upon 1 plus K2. C2 will cancel, so it will lead to the formation of C1 upon C2 plus Cc equal to K upon 1 plus K2. Here all the terms are constant, so it will give us a new constant, that is K3. Write it as a equation number 5. Now in this equation, the C2 and the Cc are the total concentration of the normal molecules and the solvated solute molecules in the phase 2. So we can simply write it as the total concentration of solute in phase 1 upon the total concentration of solute in phase 2, which is a constant term. So from this relation we can see clearly that the solute molecules enter into the chemical combination with the solvent molecules. The distribution law does not get modified, as it is C1 upon the C2 total. It is the concentration of the solute in phase 1, it is the concentration of the solute in phase 2, which is a constant, that is K3. Okay, so the distribution law does not get modified when the solute undergo chemical combination with any one of the solvent. However, there is a change in the numerical value of the partition coefficient. This K will change only, other terms will remain same. This is all about the part 3. If you people are having doubts or any queries, you can ask me in the comment section. In the next video, that is in part 3, I will discuss the important application of the Nernst Distribution Law. Thanks and have a happy learning.